So I decided to do my presentation on how animals navigate during migration. My motivation for this project is from a young age I've always wondered how animals know where to go when they're migrating, and I've always wondered how they could possibly know where warmer weather is. And so when I realized this actually has to do with magnetism, I thought it would be the perfect topic for me to explore. So how does this relate to physics? As I'll explain later on in the presentation, animals navigate through a process called magnetoreception. And this has to do with what we learned in class because we learned about magnetic fields and how the Earth actually has its own natural magnetic field. Birds and many other animals actually use this magnetic field to judge where they're going, and due to recent evidence, they may even use the strength of the magnetic field to judge where they are. So how does the Earth have its own magnetic field? So we know that a rotating electric current will cause a magnetic field, and the Earth has this flowing liquid metal in its core, and this causes electric currents. And with the rotation of the Earth on its own axis, it causes the electric currents to rotate too, and thus this will cause the Earth to have its own natural magnetic field. So how it works, many animals rely on a variety of different signals to help point themselves in the right direction, like celestial cues or even smells. However, as I said, a select variety actually also use the magnetic field. This includes birds, bees, whales, and turtles. And this ability to harness the magnetic field and navigate throughout the world is called magnetoreception. So while it isn't quite figured out how magnetoreception occurs, there are many theories for it. Some scientists believe it is due to magnetite. So what magnetite is a rock mineral with strong magnetic properties, and it's actually been found in birds, bees, and even dolphins. And while an animal can use a compass to find out where they're going, that compass wouldn't really tell them where they are. And neurobiologist Joe Kirschvink explains that the magnetite could be the material that could give them that extra info. Magnetite can actually act as a compass to show the direction of the animal and where it should be going, but in addition, it can also sense the strength of the magnetic field, and this could give additional information as to where the animal is. So while this sounds promising, so far no evidence has actually been shown that magnetite is the material that is behind magnetoreception in anything really other than bacteria. So this is a picture of the magnetite model, and this is just a theorized model, and as I said, it's not proven that it works. So the competing theory to the magnetite model is the cryptochrome model, and what a cryptochrome is a protein inside many animals' eyes. And so how it works is when a short wavelength light hits the cryptochrome, it turns it into a radical pair, which are two unpaired electrons whose spins can either be aligned or unaligned. In the presence of a magnetic field, these spins can actually alternate back and forth between unaligned and aligned. And so because the cryptochrome is inside many mammalians' retinas, it's proposed that the alternating alignments can cause light or dark spots in the animal's vision. And so this theory could actually explain a lot about how a bird's compass actually works. It explained why blue and green, so short wavelengths, actually activate the bird's compass, but red wavelengths jams a bird's compass. So this is a picture of how scientists believe that the cryptochrome model would be working. These were the radical pairs I was talking about, but as I said, this is all theorized and not actually proven. So out of the two theories I just told you, which theory is right? Recent evidence shows that Cry4, a cryptochrome gene also associated with circadian rhythm, is actually shown to increase in expression during migration season. This is obviously important because that means this gene has something to do with migration season. It also showed that Cry4 had reception at constant levels, so that means it's able to detect magnetic fields throughout the day, unlike other Cry genes, Cry1 and 2, which have been found to work more with the circadian rhythm. And so while these scientists explain that this isn't definite evidence for the cryptochrome model, is definitely more promising than the magnetite model. And as of right now, we still don't have a complete answer, but the cryptochrome model seems the most promising. So when I was talking about the light and dark spots, this is how many scientists believe it would look. Of course, we don't actually know what a bird or animal can see, so the best we can do is provide a computer simulation of what we guess they might see, which is what the picture I just showed you. So in conclusion, many migratory animals use a phenomenon known as magnetoreception. How that is done isn't quite clear, but there are two theories, the magnetite model and the cryptochrome model, and as of 2018, evidence heavily points towards the cryptochrome model, but we can't be completely sure. And these are my references.